In practice, the zenith distance, D or D, is not measured, but its complement. The altitude angle is measured. So the elevation angle is measured, and the zenith distance is the complement. So you need a box for that, and you need that right triangle up in the sky. Zenith distance is determined by substituting the measured altitude in the equation. Zenith distance equals 90 degrees altitude. Now, last time we did angles, we showed that it's not an acute angle, it's not an obtuse angle, but it's 90 degrees, which can only be one thing, a right angle. They're stuck with it because all of their books say you subtract from 90. So no matter how much they fight about right angles, sorry, boys. Figure 15 shows the relationship between altitude and zenith distance. If the altitude angle H in figure 15 is 50 degrees, the zenith distance is 90 minus 50, or 40 degrees, which expressed in nautical miles is 2,400 miles. That would be your zenith distance, 40 times 60. The explanation of why, this is where everyone needs to pay attention. The explanation of why the sextant measures altitude instead of zenith distance lies in the fact that the early instrument makers quite logically designed their instruments to measure altitude because the instruments had to be leveled on the visible horizon. Flat baseline, not curved adjacent. There being no definite point which marks the observer's zenith. So what he's saying here is if you're on the boat, how do you know what your vertical is if it's tossing and turning? There's no marker for that. But if you tie it into the visible horizon and do dip correction, you're going to get your baseline and get your 90, so you got your zenith automatically once you do it. For uniformity of practice, artificial horizon instruments were built to measure the same coordinate. Though the gravity-operated mechanisms of these instruments indicate the vertical, the observer's zenith, as well as the horizontal. You see, that's why with the bubble sextant and the artificial horizon, you've already established horizontal, especially, I mean, you've held the spirit level in your hand, you put it on the table, you know what that's telling you, and since everything is a right angle, then you've established your zenith. But not at sea, because you can't get your vertical at sea, you gotta get your horizontal first. That's why you do dip correction, and that's why it's called sea level. This destroys them. The instrument is designed to work over flat surfaces. It cannot work on the curved adjacent. I'm done. So this is what they're saying is happening. You can see a right angle from the center of a presupposed Earth, and it's always subtracting from 90. And you could see the elevation angle, and you could see the zenith distance to complement. Everybody tracking with that? Yes?
Just put it up big for the audience. But yes.
Got it.
All right, just let that sink in for a minute. Then you could, so this is what they're saying is happening. Now let's go to the next slide, please.
Okay, is this the one with the scribble of a guy?
Yep.
Yeah, okay.
So there's an angle of elevation and angle of depression. We're going to see several slides here, and this is no different than the zenith distance being described to us that works on a flat plane, because obviously you can't get an elevation angle with a curved adjacent. And the complement is the zenith distance, which is the angle of depression here. So here's the sun, B, and here's a scribbled person with a sextant, let's say, and he's at C, and he needs the right angle to get this angle of elevation. Well, the complement angle would be the zenith distance of the sun's GP to the person's GP. Next slide. So angle of depression and angle of elevation are equal in this. So what do you need to have an angle of elevation? You need a baseline, horizontal line, level. What do you need to have an angle of depression? The same baseline, but in the air.
Yep.
you need a reference. It needs to be relative to something. So here's a plane, say at 30,000 feet, and in order for that angle of depression for the plane, it needs to be a right angle as well. Next slide. Again, showing in this illustration a line of sight, which is the elevation angle, and then the complement angle would be the angle of depression, or in sextant jargon, the complement or the zenith distance. You need a flat line up there, another right angle. Next slide. You're at war. There's a submarine coming at you. You want to find out where it's at. You have to treat the surface of the ocean horizontal, flat, level. You need a right angle. Target that sub. Next slide. You see the hot air balloon. You see the horizontal baseline needed for the observer to get the angle of elevation. Well, if the observer was in the hot air balloon, they need a horizontal line to get the angle of depression. And in sextant jargon, that would be zenith distance for the person on the ground. Next slide. Elevation and depression angles. Elevation is the angle up from the horizontal. Depression is the angle down from the horizontal. Pretend the guy is the sun or a star or a moon. It's easily the same thing. You need straight lines to get angles. Next slide. This is a kind of a weird image because it's not coming in clear, but you got a jet fighter targeting a ship. Same thing applies here. Next slide. Here's a theodolite with a plumb bob needing to get a horizontal, and getting the angle of elevation is based on achieving a horizontal flat baseline. That's why you do dip correction when you use the natural horizon and you don't with a bubble sextant or artificial horizon, because you already have established the horizontal with those two methods. But the complement would be the zenith angle. Now we just saw, in order for the zenith angle to work, it needs a horizontal as well, but in the sky. Next and last slide. Azimuth and altitude for northern latitudes. You can see here the equatorial plane, flat baseline, a circle. There's your horizontal. And then you get your angle. And then you see where it says altitude. Well, so that's your elevation angle. And then you see where it says vertical and zenith. Well, that's your complement. So your zenith distance would be gotten from that, the remainder. So that vertical, you have to draw a straight line to the sun. That has to be a horizontal all the way to the sun for that angle to even be there, as we saw in the previous slides. This curved meridian is a joke. It can't be curved. It needs to be horizontal for a zenith distance. Any questions?
No.